All right, so this is a pretty complicated one, but it's nothing too difficult. So we'll draw two graphs, but first we'll go over the question. So it's saying mercury is poured into a U-tube with two cylinders. They have both different radii, right? And as well, we have the given radiuses, or radii of each arm, the mass of the water poured into the tube, and as well, we have the density of mercury. Cool, so let's begin by writing everything. So I'll denote the radius, or the image. So we have a U-tube, right? And both have different radii. Of course, the numbers might be similar, but let's exaggerate the image for the sake of understanding. That's too exaggerated. Okay, there you go. Get that. So there's that opening. So we'll denote this as opening on the right and opening on the left. Now with this image, we can see that, I don't know why, but I'd imagine mercury to be purple. I don't know if it is, but let's draw it as purple. So this U-tube at equilibrium, so this is the equilibrium line. And we'll also denote this as phase 1, or stage 1, what that? Stage 1. So at stage 1, when it's at equilibrium, we're at this line. So nothing has happened to the system. This is purely equilibrium, right? But then we transition into stage 2. And I think it helps to have multiple images just to make sure you know what's happening. So, of course, this. And the same EQ line we'll write, or the old EQ line. So we'll write that as EQ prime, or the old equilibrium line. Right? And so what we have here in a new image is this. So it told us that 110 grams of water is poured into the right arm of this tube. Now, once this entire system has settled, it will look something like this. Right? So now it's asking us, read very carefully here, asking us, what is the height h above the mercury level on the right arm? Does the mercury rise on the left arm? So basically it's asking, what height h above the mercury level on the right arm does the mercury rise on the left arm? Now what is this telling us? Well, let's start by denoting a bunch of variables. We have the height of the water. We'll denote as capital H. We'll denote this part right here as the amount it sunk, and we'll denote this height as the amount it rose, right? So what it's asking us is, we'll make another two lines using, let's say, this one, this color. So we have this new line here, and of course this new line here. Okay, so it's asking us for this total change. We'll call this little h. So it's asking us to what level, of course h, does the left arm rise with respect to the the right arm, right? So this question is simple in theory, but the wording always gets confusing. So we'll just begin. Now, if you want to figure out h, we need to make a few equations for ourselves. So from this image itself, we see that h is equal to the amount it rose by plus the amount it sunk by. Now, the only reason I put magnitudinal signs, because some people might denote this as negative measurement. It went negative meters down, right? Which makes more sense than 2 meters, because then you have to denote kind of the direction, right? So the magnitude of the amount it rose plus the magnitude that sunk, right? So to begin, you always begin with a kind of a conservation statement. So of course we have this statement, but we also have that the pressure on the left should equal the pressure on the right. Now what does this mean? Now we see here, at this point right here, we have a homogeneous solution, or homogeneous liquid. All that means is that the liquid on the left and the liquid on the right below this line is the same liquid, which means it behaves the same way. Now what does it mean for us? Well, it means the pressure on the left, the only pressure that exists on the left side is of course the atmospheric pressure, and also this part right here, this entire part. And now what is this part? Well, this is the pressure due to mercury, right? So on the left side we have atmospheric pressure plus the rho of mercury, or the density of mercury, well, times the gravitational constant times r, we'll say, right? Because that's how much it rose by. Or sorry, we'll do it as h. from the homogeneous level. And on the right side, of course, it's atmospheric pressure because both interface with the surroundings, at both points right here. But it's also water and this height here, right? So this would be plus the rho of water times G times capital H, right? Now from here we see that this cancels out. G is a common factor. Now we get that H is equal to rho of Hg, rho of water, rho of Hg times capital H. Cool. Now the issue comes, how do we get capital H? Right? So immediately this might look weird. Okay, let me move this. Okay. So now, of course, we have equation 1, right like that. And we have equation 2. So now how do we get capital H? Well, bear with me here. We know that density is mass over volume. Now look with me here. The volume taken up by water is the H, right? The height, times this part, which would be the base. Now what does that mean for us? Well, it means that our volume is mass over H times 2 pi r squared. And what would this r be? It'd be the radius of the right opening, right? And from here, we can just isolate for H because we know the density of water. We also know the mass of water, and we know everything else. So here, H becomes the mass of water over the density of water times 2 pi times the radius of the right opening squared. Right? So now we get that according to this equation 3. So we'll 3. We'll combine equation 2 and equation 3 to give us H is equal to the rho of water times the rho of mercury times the mass of water over the rho of water times 2 pi. So here, see that these cancel out, and we get that our final equation is the mass of the water all over the density of mercury times 2 pi times r squared. So for a general equation, it's just be 1 over 2 pi times mass over density times r squared. So this is our final equation. All you have to do is plug in and you get the H. But fundamentally, this entire problem is based on pressure equality. So we know that pressure is always constant. Thus, the pressure on the left side, pressure on the right side. So it becomes a matter of recognizing that you always have atmospheric pressure if you are in contact with the air. And you also have the pressures along the interface. And you'll see that word a lot.